Welcome, my name is Jonas. I'm developer and co-founder at Flying Shapes. We are a very young startup, just working since about half a year on a product, which is, so in principle you just saw how virtual reality enables us to have a nice look at the CAD data and to evaluate it and to have quality assurance in VR as a totally different perspective from the past. And we are actually touching a different position at the design process. So, I mean, the quality assurance is at the very last stage when you have your final CAD data and you just want to evaluate it. And we are actually working on a product that enables you to actually create this CAD data. So the idea is that classic CAD, classic computer-aided design software, is kind of intellectually challenging. I mean, you have a two-dimensional screen which shows you actually the projection of a three-dimensional object. So you see maybe this car or whatever you're designing from the side, from the front, from different views. But then you have to use your intellect to imagine how this shape would actually look like in real world. And well, depending on that, I mean, we have now two-dimensional input. You're working with the keyboard and with your mouse, which is optimized for this paradigm, for this two-dimensional output. Okay, you have these 3D mouses that are quite useful, but it's still something different. It's just optimized for, well, you have a screen. And we think our vision was, well, just use VR, use it as a tool to enable you to have a three-dimensional input. So you can use the controllers and directly you move the shapes, the control points, the curves, the way you want to have it. So you directly touch your object, which is visualized stereoscopically in a very realistic way, and you can directly move it in the way you want, and you permanently, directly get this feedback, which is already really, really realistic. So that's how our tool, our product looks like. So that's one tool, very, very simple. It's just a sketching tool which enables the designer to roughly sketch the idea into the room. So this is really just like a pencil, nothing special. We've seen that in many different other programs, so that's nothing new. But in the next step, the designer then uses these sketch lines to create some actual CAD data. So he moves these control points directly in 3D space. So he can grab it and move it wherever he wants to have it. And while doing it, well, he really knows how this shape looks like. He doesn't have to think of, okay, if I look at it from top and from the side, the shape would be like that. No, he just can move his head and decide if this is the shape he wants to have. Then in principle, based on these curves, you can create patches, but instead, I mean, we have now this three-dimensional input, so we can have a completely new paradigm. So we developed a tool, which we call a patch tool, which feels like you have some piece of fabric and you just stretch it over the air, in the space, and you can create the shape you would like to have. And while doing it, once again, you permanently have this feedback that the shape really looks the way you want to have it. And in case it's not perfect at the first shot, well, of course, it's CAD data, so again, you can touch it, adjust it the way you want. And here you see the control points. And we also have a history base, so when you touch one patch, the whole other patches which are connected to it move the way you would expect. One major decision we took, talking about UI, is that we have different tools. So in the VR, it feels like you're using a specific tool for a specific task, instead of using a lot of menus, for example. So if you want to draw your sketch, you choose this orange tool, and if you want to draw a patch, you choose another tool, and you have the left and right hand with two different tools, so you can work at different parts at the same time. So here in principle would be a video, which well now doesn't work because I don't have the cursor. So what it shows is actually that we've been inspired by budget cuts a bit. So that's a really nice VR experience. I think everybody should play that little game. It's not only a demo so far, but really, really love it. And based on their idea, where you can choose a different weapon in principle, you grip, you press the button on the side, and you move to the left and right to choose a different module which is attached to your controller. And based on that, we developed a functionality which we call this tool revolver, which is optimized for speed, because we develop a program which is made for specialists. So it's not a game. So it should be efficient as possible, as fast as possible. And also, we enable the user to really choose this tool blindly, so he doesn't have to look at his hand. So it works is that once you press this menu button, you see this view, and then you can just rotate your controller, and you feel a click, a feedback, once you change to another controller, and once you release the button, you have a new tool. And left and right hand are separately. Well, then we spent quite some time about the UI. What button should do what? And we were really wondering, everybody who uses a new tool at the desktop is standard program, at some point he tries to press Control-Z to undo something. So we just wonder, will there ever be such a standard in VR? And to us, the most natural way to do an undo was to do a horizontal swipe on the Vive. So on the Vive, we're using the touchpad, and if you have your thumb and move it to the left, it's an undo, and if you move it to the right, it's a redo. And it feels very natural, and I already saw some people trying it out without me having told them that. So that's our way to do undo, and maybe I'm looking forward to see how this will look like in a few years. Additionally, as I said, we have this tool revolver, we have a vertical swipe, which is just generically, we change a parameter. This parameter depends again on the tool you have selected. And click is, if you click the button on the touchpad, you can select objects, and then again, depending on the tool, you can do different things. And then we're using the trigger to grab objects or to activate the tool, so to draw lines or to create patches or to trim a patch or whatever. And then we use the grip on the side to actually, and this is always the same, independent on the tool, it grips the whole scene. And that's something that really feels awesome, because you can use your left hand to grip this object, and then with your right hand really work on this object you're designing. Okay. And if you're gripping both hands at the same time, it's like on a touchpad multi-touch, you can scale your object. And it's not like tilt brush, it's similar, but what we did is like you can actually rotate the objects at the same time, and it feels really very natural. So a few words about the technology we chose. So first of all, we're using SteamVR. First of all, of course, because we just began developing for the Vive. But also, using SteamVR, you are hardware independent, and for us as a small company, we can't afford to have an Oculus and a Vive team separately, so that's a lot of a good thing for us. SteamVR runs also on Linux, and we are two physicists, the developers, so we are really keen on working on Linux, and because it boosts our productivity. So it's still better. It doesn't run very well, but at least it runs. The only disadvantage here is vendor dependent, so we're looking forward to see some more open VR implementations in the future. We also chose to use Unity, as a lot of people do here, but actually for us it was quite a long process. We started with CryEngine, worked on that, had a lot of issues, moved to Unreal Engine, was way better, but still some compiling issues. We had the feeling that Unreal is not really made for programmers. They are more like focusing on people using this blueprint, and so often we had to restart the engine. That was really weird, and we talked with a lot of people, and nobody could help us. So then we had a project with Godot. It's an open source engine, which is really awesome, but it's really not. It doesn't support VR, so it wasn't worth it. And in the end, Unity, and really we fell in love with that. It's platform independent, so it's also running on Linux, not perfectly, but pretty good. The community is huge, so we get a lot of feedback there. And the language, we really fell in love with the language. We are low-level C programmers originally. I have a lot of experience with also Lua and Python. But C# is really a good mixture of all of that. And it has a just-in-time compiler, which again boosts your productivity, because you don't have to wait for compilation, because your tool just runs if you start it. A small disadvantage was that we didn't find any good math libs in .NET, so we had to, actually we decided to implement everything on our own. The alternative would be to use some C libs and import these DLLs, which of course also works. When we started with this project, which was December last year, we of course prepared for that, and we had a look at a lot of YouTube videos and publications. And of course we learned a lot about VR sickness in theory. But it turned out that while developing it and showing it to people, we learned a lot of things we didn't find in the web. So that's something I would like to share with you. So first of all, I mean, there's a rule, keep your FPS high. Well, that's nothing new to you. However, how do you do that? And I think in our specific case, we found a way which is, well, something we didn't see yet. Additionally, you should properly measure your FPS, your frame rate. So you don't use like the output from Unity or something, because it's lying to you. It just tells you an average of the last, I think it's 3 seconds or something. But what does it mean? It doesn't mean anything at all. It could be that like every frame is perfectly fine, but every now and then you have a very bad frame. And this frame might be enough to make you nauseous. Okay? And we found out, so just measure all your frame times, and that's what you're doing. We're permanently streaming data, every frame, how long it took, and store it in a database, and then we do some analytics on that, and we see like, if you have like the 99th percentile above, 13 milliseconds per frame, we are fine, and otherwise we get an alert. And then there was another thing, reducing controller jitter helped us a lot, fighting VR sickness. So you always have some jitter, and by reducing that, we really found that VR sickness got much better. More details on that. So first of all, keep your FPS high. So there's a standard way in game design, you just change the level of detail. So that's nothing new. And what typically it's like if you have a model, like a tree or something, so if the tree is very close, you render it in the highest resolution. And if the tree is far away, you just reduce the resolution. Pretty easy. So you decide this depending on the distance. This, however, doesn't work for us, simply because we don't have any static objects. We have patches, shapes that are created by the user. And so the user could create a small shape, you could create a huge shape. So the distance alone isn't enough. So what we're doing is we're permanently measuring the visual angle of the objects. So like here in this example, you see 2 objects which have different sizes and different distances, but in the end, they have the same visual angle. So they should be rendered with the same resolution. It's in principle very easy to understand. So we're using this parameter together with the current frame time. So we're looking at the frame performance, and when we see that we're getting close to only like 80 hertz, 80 frames per second, we slightly reduce the level of detail of our objects, which is very easy for us because we are CAD, so it's easy for us to calculate the mesh based on the CAD data. Then concerning this jitter I talked about, it's very easy to understand that you always have jitter in your controller. First of all, of course, due to the tracking, and second, I mean, you hold, as a human being, you hold this controller, so you cannot hold perfectly still. So in principle, it's not an issue. If you have your HMD on and you see your controller, it doesn't move much. It feels natural. However, in VR, you are able to grab huge objects. And this accelerates the movement. So when I talk about jitter, of course, first of all, you have a movement jitter, but you also have a jitter in your orientation. And this orientation is the issue here. So you have some small angular velocity, which is omega here. Well, but then, if you grab an object, the speed of any point on this object, like here in this example, this point over there, depends on the distance to the axis, so in the end to the controller. So if you have your controller like here and you're grabbing an object which is in front of your eye, this will move a lot because the movement is accelerated. It's a very easy math. And that made me really nauseous. It doesn't feel very good. So in the end, what we tried to do and what we did is some jitter compensation. And there are a lot of algorithms. And the first one, without even reading, I just tried it out how it feels. It's exponential smoothing. I mean, it's really as simple as this line. That's all you have to do pretty much. And this already this already fixed our issues. So it's really easy to do. However, there's a slight issue with that. How it works is like you have your controller position right now, and you have your object position from the last frame. And then you calculate the new position, or orientation in this case, of your object by just having something in between. And this how far in between is this smoothing factor over there. And if the smoothing factor is like very large, it means like if I pull an object like here, it lags behind, okay? And this doesn't feel very good. So by tuning this parameter, it typically was already, we fixed that issue. But you can have a perfect jitter compensation by typically use the Kalman filter, which is a very common algorithm. If you read the wiki article or something, it sounds much more complicated than it actually is. So it's a bit harder to implement, a bit more than only one line. But still, it's easy to test it. You have way better results. But in the end, it turned out that there is another algorithm, which is just double exponential smoothing. What you have there is like, you have in principle 2 parameters, and you just add a second parameter which just tries to predict the future of the object. And then in principle, you have 2 times this line here. So the performance is still very good, but the results were really perfect for us. And it's still quite easy to implement. However, if I write here the performance is a factor 20 less, well, it means we're talking about something like 100 nanoseconds over there and something like a few microseconds over there. So it's still negligible for VR for most cases. Then a few words. When we showed our product at April at the CeBIT, many people asked us how we managed to develop such a project in such a short time. So I'd like to share something about productivity, how we boosted our productivity. So when we started, we had only 1 Vive, but we had 2 Vives. We were 1 product designer and 2 developers. So it was clear that the product designer has to use a Vive. I mean, he has to use the tool and decide if it's the right thing, if it matches the needs of the designers. So the developers, in the end, we the developers, only had 1 Vive. But it turned out that the process, the developing approach we took meant that actually nobody uses the HMD. So why is that a good idea? I found a paper which compares Emacs to Vim. So the efficiencies of Emacs to Vim. Who doesn't know that? These are 2 text editors in principle that are very common within very often used within coders. And the reason for that is, for example, they are optimized for movement. So for example, they are optimized not to use your mouse. You keep your hands on your keyboard and you don't have to move your right hand to your mouse, because that's a lot of time waste. You waste a lot of time by this movement. Yeah, for some people it feels stupid, but actually it boosts a lot your productivity, because you can focus on programming and don't have to look like that and get interrupted. Now think about, I mean, if coders think like that and they are keen on these tools, yeah, how would it look like when you're coding like that, then move your HMD on, test something, move it off again, try something? It kills your productivity. So we thought, like, okay, how can you fix that? And once again, as so often in computer science, the answer was test-driven development. So test-driven development, in principle, the idea is you always go through this circle. You think of, maybe you have a bug, so then you write a test that reproduces this bug. Then you try to fix this bug, so you go from red to green. If it's fixed, you refactor your code, and you go on and on and on like that. So for us, it meant, well, we just had to write some code which simulates the movement of the user, and then we wrote tests that do the simulation, and we say, okay, well, if the user does this and then that, we expect then the object looks like this. And we wrote a test-driven development framework for us that helps us this. And due to that, we really don't wear the HMD. Well, not at all. Of course, sometimes, especially if we developing new tools, new parts of the code, we have to test it how it feels. But once we're done with that, we try not to use it as much as possible. And so it boosts your time. The quality of the source quality, the code quality is way better. And also, I mean, test-driven development anyway is such a good thing because I think it's the best way to document your code. So that's all from my side, and I hope to see you later at the happy hour.